Yes, welcome everyone. I'm very happy to introduce Grani Hanasusanto today. So he will speak about distributional robust path integral control. He's associate professor at the University of Illinois. His research is focused on decision making under uncertainty. So for me, he's well known for his works on K-adaptability in robust optimization and distributional robust optimization. And yeah, he won several prizes. He's currently associate editor at the Informs Operation Research Journal. So I'm very happy to have you here, and please.
Yeah. Thanks, Yanis, for the kind invitation. So today I will present this recent work on distribution robust path integral control. This is a joint work with my students Hyok Park and Dojo, and also my colleague Takashi Tanaka from UT Austin, who is an expert in control theory, and he's the one who introduced me to this topic of path integral control. So these days, autonomous control systems are becoming more pervasive in our society. So these are engineered systems that are designed to perform well under complex and uncertain environments with little to no human intervention. So advances in technology have accelerated the progress of these systems. And as shown here, Boston Dynamics Atlas can move like human. And then Tesla's autopilot can drive your car in complex environments. However, as illustrated in these clips, these autonomous systems may not always work faultlessly. So the robot here is failing even in the same environment. And then reports of fatal crashes involving self-driving cars are not uncommon. So it leads us to question whether we can trust these autonomous systems for safety critical missions. And furthermore, this recent article claimed that the way we train autonomous systems is fundamentally flawed. So we tune the algorithms to achieve near perfect performance in simulator or lab-like environments. But when deployed in real world, they tend to perform worse than our expectation. And in the worst case scenario, this may lead to catastrophic events. So many researchers have been paying attention to robust algorithms or controllers to ensure safe performance. And our approach in this talk is part of these efforts. Specifically, our approach combines distribution robust optimization with an interesting control framework called path integral control. So we name our approach distribution robust path integral. And our contributions lie in developing safe controllers with theoretical performance guarantees under some settings, and a tractable solution scheme for quite general nonlinear control problems. So let me introduce our problem setting. Before formally defining our problem, let's quickly discuss the essence of stochastic optimal control. So here we consider a continuous time and continuous space stochastic system. And at every time point, given the current state, we would like to determine a control action that optimizes the expected total costs over the remaining time horizon. So for example, here we have a robot navigating a 2D plane environment. And in this example, the state space can be the robot's XY coordinate. And additionally, there is some noise, a stochastic process with probability law P star. And the robot's task is to navigate to the goal as quickly as possible while avoiding an obstacle, like the black square in the middle here. And relating to the safety critical missions in our introduction, hitting the obstacle can be viewed as a catastrophic event. And therefore, our objective is to learn an optimal policy that strikes a balance between speed and safety in control performance. So in this talk, we consider a control affine system over finite time up to capital T. In this control affine system, we can split the system dynamic into uncontrolled dynamic, the control part, and the noise part. And specifically, the uncontrolled dynamic is a general nonlinear function of an n-dimensional state. And our dynamic is linear in the p-dimensional control input U and noise Xi. So here U and Xi are multiplied by this matrix G. This is an n by p matrix valued function that maps the control and noise to the state. And furthermore, the noise Xi is multiplied by a constant p by p full rank diffusion matrix. So in this case, sigma times sigma transpose can be interpreted as the covariance matrix of the noise. Now, this control affine system is quite general. In fact, it can represent many mechanical systems, such as the humanoid robots that we saw earlier, and also the autonomous cars. Now, the noise process here is a multivariate Wiener process. It's a drifted Wiener process consisting of the drift term mu and a standard Brownian motion W. And in this talk, we assume that the probability measure P star that govern the true noise process is unknown, while the function f, g, and the matrix sigma are known. So this setting is realistic in many real-world systems where the dynamic itself is well understood by physical laws, but the noise is hard to model accurately. So now viewing the stochastic system as constraint, we can formulate our stochastic optimal control problem as a constraint optimization that minimizes the expected cost function evaluated under the probability measure P star. So the cost function here consists of two parts. So we have the running costs and the terminal costs. Now the running costs consists of state-dependent costs and the control costs. U transpose RU, which is quadratic. So we assume that the control is a quadratic function where R is a positive definite matrix. And the terminal cost here is a nonlinear function in the state. So for example, this allows us to use indicator function to denote the event that the robot has not reached the goal at the terminal time. So we face two challenges in solving the problem. So the first challenge is that our stochastic optimal control problem includes general nonlinear cost function and dynamics, which makes solving the problem difficult. And then the expectation here is evaluated under P star. So that's the second challenge. So getting the optimal policy, of course, requires knowledge about the the probability distribution, which is not available by our assumption. So we lack crucial information to solve the problem. Now, to address the second challenge, we adopt this distribution robust optimization approach. So we assume the availability of a nominal probability law Q, and using Q, we can formulate this distribution robust version of the stochastic optimal control problem. And let's call the problem the distribution robust control problem. And here, our ambiguity set is given by the Kullback-Leibler ambiguity set. So this set contains all probability laws that are gamma distance away from the nominal one in KL divergence. Now, the min-max problem is difficult to solve directly, but as shown in this lemma, we can obtain a single level minimization problem for the distribution robust control problem under a mild assumption. We have an interesting observation. So here, the reformulation is very similar to a classical control problem called the risk-averse control, where theta is a fixed parameter, right? In our case, we jointly optimize the risk aversion parameter theta and the control policy together. But the important point is that this similarity between the two problems allows us to efficiently solve the distribution robust control problem using the path integral control method. We will discuss this path integral control later. But before that, let me briefly explain the risk averse control problem. For a fixed risk aversion parameter theta, we have this problem. What we essentially do is just we exponentiate the cost function multiplied with the reciprocal of the parameter theta. And then we take expectation. And then the remaining log term multiplied with theta sort of scale back the expected exponential costs. Now, this parameter theta controls the risk behavior of the optimal policy. So a high value of theta will bring the costs the rates of the cost close to zero. And the function becomes approximately linear. And we get a risk neutral problem. On the other hand, a small theta will enlarge the range of the costs, and the exponential effect becomes more prominent, and we will penalize large costs more severely. So as a very simple example, let's say we have two policies, U1 and U2. And suppose these numbers are two possible costs under each of the policies. So for example, under U1, we have two costs, 0.1 and 1.1 with equal probabilities. So the mean cost is 0.6. Whereas under U2, we have costs 0.9 and 1 with equal probabilities. So the mean cost is 0.95. So on average, U1 gives a lower cost than U2. However, the largest cost under U1 is 1.1, which is larger than any cost under U2. So we can compute and compare the exponential cost under the two policies. And let's see how the choice of theta plays out for the optimality. So for large theta, U1 is the optimal policy because it has a lower objective value of 0.61 versus 0.95. So for large theta, we prefer the policy that yields a smaller average cost. On the other hand, for small theta, U2 becomes the optimal policy. And this is because U1 has a 1/2 probability of generating the worst cost of 1.1. So for a lower value of theta, we will penalize the policy U1 and prefer policy U2. And this indicates that a lower value of theta yields a more risk-averse optimal policy. Okay, so let me next briefly discuss the literature. So we are not the first to observe the equivalence between distribution robust control problem and risk-averse control. These two papers have drawn connection between the two problems. However, their setting is discrete time, while ours is continuous time. Then the three papers in the middle, they showed that stochastic optimal control problems can be reformulated as a path integral control problem under certain conditions. And basically, the path integral control formulation reduces the minimization problem to simply an evaluation of the expected costs under uncontrolled dynamics. And then these three papers on the bottom, they showcase applications of path integral control in the context of robotics. There are other papers that I don't list that apply path integral control to other real-world applications, including autonomous driving cars that we saw earlier. All right, so let me now introduce the algorithm. This is a quick overview of the algorithm. So using the equivalence between the two control problems, we can decompose the reformulated distribution robust problem into a master problem and a sub-problem. So the master problem contains a simple linear function, gamma times theta, and this function g theta, which is the sub-problem. And this is our risk-averse control problem for a fixed parameter theta. So the nice thing about this decomposition is that the master problem is just a univariate optimization problem over theta. And if we know the function g for any fixed theta, then we can easily solve the master problem using many different methods like bisection. Now, the remaining work is just to solve the subproblem for fixed theta. And as I mentioned earlier, the difficulties come from the nonlinear cost function and the dynamics in our problem. And we will now discuss how the path integral control allows us to solve the subproblem efficiently. Okay, so to obtain the reformulation, we will first derive a dynamic program. So we can recursively define the value function j for all state-time pairs. So this function is a scalar function that depends on this state and time pairs. And on the right-hand side, we have this risk-averse control problem starting from state x and time t, which are the inputs to the function, to the value function. Now, obviously, when the function inputs are the initial state x0 and time 0, then the function represents our original risk-averse problem. And so this value function essentially represents the best possible cost that we could obtain starting from any given state and time. Okay, so this equality, we simply substitute the definition of the cost function. We have the running costs and the terminal costs. And then we split the running costs into two parts. So we have an intermediate time, t plus r, and then we integrate from time t to t plus r, and then we also have the integration from the intermediate time, t plus r, to the terminal time, capital T. So then we see that this expression is simply the value function at time t plus r. Okay, so we obtain the dynamic program recursion. And then next, we are going to take a limit. We bring r to 0. And then we derive this PDE, which is the Hamilton-Jacobi-Bellman equation. So here on the left-hand side, we have the partial derivative with respect to time t. So this is just a scalar. On the right-hand side, we have first-order partial derivative with respect to the n-dimensional state vector. So this is a vector. And also we have this second-order derivatives. So this is a matrix. And this is, we have a quadratic term, right? So we have the partial derivatives transpose this matrix, transpose the partial derivatives. So this HJB equation essentially means that if we can find the solution J that satisfy the equation, then we basically solve the risk-averse control problem exactly. And of course, from the value function, we can obtain the optimal policy. However, unfortunately, solving this HJB equation using the dynamic programming approach suffers from the curse of dimensionality of state space. Yeah, so we solve this backward from the terminal time to the initial time, and the solution time will be quickly become intractable as the size of the state space increases. So the good news is that we are not going to use the dynamic programming approach. So under a certain condition, this HJB equation can be converted into a path integral control formulation. And this formulation allows us to reverse the direction of computation. So we can actually evaluate the value function at any arbitrary time and state. And we don't need to solve this backward induction for all state time pairs. And instead, we can actually compute the value function on the fly for any given state and time. So to be able to apply this path integral control, we need to obtain a linear PDE. So the term I highlight here is nonlinear because it is quadratic. But if this condition is satisfied, then we can linearize the term, right? So this term will vanish if there exists a theta such that this covariance matrix is equal to theta times the inverse of the control matrix cos. So this is a standard assumption in the path integral literature. So the intuition behind this assumption is that since the weight control matrix R is inversely proportional to the variance of the noise, control input that is affected by high variance noise would have cheap control costs, while a small variance control input has high control costs. From a control theoretic standpoint, this makes sense because under a large disturbance, a high variance, then a large magnitude of control input is required to bring the system back to a desirable state. All right, so now this is the path integral formulation. So this says that if the condition is satisfied, then for any fixed risk aversion parameter theta, we can actually compute the value function in closed form. Yeah. So we just need to evaluate this expectation. And notice that this value function no longer has minimization, right? It's just an evaluation of expectation. And so here, the subscript in blue means that we do not inject any control input into the system. Okay, so in other words, the control input is just a factor of zeros. Okay, and then the corresponding cost is uncontrolled costs. Okay, so this value function, which is originally it was a minimization problem, becomes an expectation of the uncontrolled trajectory costs starting from any given state time pair. And then furthermore, the optimal policy can also be obtained by simply multiplying these matrices with the partial derivative of the value function. However, we should note that the evaluation of the expectation is not easy, of course, because there are infinitely many possible trajectories in this continuous state and continuous space, continuous time space. So in the numerical experiment, we utilize the Monte Carlo sampling method to approximate the expectation. And then we further discretize the time interval, which yields an approximated value function, as well as an approximated optimal solution. Okay, so getting back to our algorithm, again, we have decomposed the single level problem into two parts. The master problem contains a simple linear function, gamma theta plus this function g of theta, which is the risk averse control problem in this the sub problem, right? And we will solve this using the path integral method. Yeah, so we will basically we will solve this expectation, evaluate the expectation approximately via the Monte Carlo sampling and time discretization. All right. So this is the pseudocode of our algorithm based on discretization of over state and time space. So we discretize the continuous time space into small time steps with some interval delta t. So practically speaking, delta t can be thought as the required time for a sensor or agent to observe the next state. And then for discretizing the state space, we use the Monte Carlo method. So specifically, we generate m number of uncontrolled sample trajectories. And then we compute the trajectory costs, the corresponding trajectory costs. So for example, here we have these three uncontrolled trajectory costs. The green trajectory ends up being away from the goal. So it incurs the cost, let's say 200. The orange one, because it hits the obstacle, a huge cost is assigned to the trajectory. The last one gives a nice trajectory because it ends up close to the goal. So the cost is small. And the remaining step now is just to solve the distribution robust control problem using decomposition. So for the subproblem, we approximate the value of g theta using the Monte Carlo sample average approximation. Whereas the master problem will be handled by bisection, which gives us the optimal theta star. Then the optimal control will be computed using this formula. So here Ri is the normalized trajectory cost, whereas this epsilon I is the ith noise sample. So by construction, the noise associated with a smaller trajectory cost will have a higher weight. So if we think about this example, the nice trajectory will contribute more to the optimal control than the other two trajectories. So the optimal action will be steered toward that direction. Good. So this is just a quick demonstration of the algorithm. So the robot is trying to navigate to the goal while trying to avoid this obstacle. We remark that these trajectories are generated independently, right? So this is an advantage of this path integral control. We can actually harness modern GPUs, which can generate large number of trajectories in parallel. Okay? And this parallelization can significantly speed up the computation process and also enhance the practical applicability of the approach. Okay, so far we have assumed the availability of nominal noise process. So now we move on to the data-driven setting, where we construct an estimate of the noise process in a data-driven manner. So here, the distribution robust path integral control has some theoretical performance guarantees, which provide guidance in determining the value of the radius gamma. Okay, so let me explain the data-driven setting first. So here we assume that we have collected n IID trajectories of the noise process over interval delta t. And then taking average of the samples, these empirical noise trajectories, we can obtain the empirical drift term, mu hat here. And then we can construct the approximate noise process, psi hat. And let me denote this probability law p hat defined by this approximate process to be the empirical probability law. And then going back to the distribution robust control problem, we could construct the ambiguity set where we replace the nominal probability Q with p hat, right? And then we hope that the ambiguity set contains the true probability law p star. But of course, we cannot guarantee this for sure because the ambiguity set is a random object, right? So the construction of p hat depends on the realization of the data, and different sets of data can give you a different ambiguity set. So we would like to obtain a probabilistic guarantee of the containment of this p star in the ambiguity set. And to obtain the result, we will make use this Girsanov theorem. So as you may recall, this term appears in the KL divergence. And Girsanov theorem provides an analytical formula for this likelihood ratio between two probability laws, P and Q. And suppose that P is defined by this stochastic process with drift mu1, whereas Q is defined by this stochastic process with drift mu2. Then the likelihood ratio between the two probability laws is given by this exponential term of these two integrations, where the first one is the Ito integral, which is random process, whereas the second one is the deterministic quantity. And then applying the Girsanov theorem, we can obtain this guarantee that the true law is inside the ambiguity set with probability at least 1 minus 2 exponential minus gamma n over square root p, where n is the number of trajectories, whereas p is the dimension of the noise process. So let me quickly show you the proof. So the true probability law P star belongs to the ambiguity set. That implies that the KL divergence between P star and P hat is less than gamma. Now, by Girsanov theorem, you have the formula for the likelihood ratio, right? And then applying the logarithm, you will get this integrals. And then the integral here is just the expectation, right? And then since W here is a Brownian motion, the expectation of the first integral becomes 0, and the KL divergence simplifies to the expectation of the second term, which can be reduced to this quantity, right? And then we use Hovding's inequality for Gaussians to obtain the probability that the squared error between the empirical estimate mu hat and the true mean value is less than gamma, okay, which is given by the right hand side quantity here. So this completes the proof. Okay, so we have the containment guarantee, and then we can also use this result to obtain out of sample performance guarantee for our data-driven distribution robust path integral control problem. So suppose Z hat and U hat are the optimal values of the data-driven distribution robust control problem. Then setting gamma to this value on the right-hand side, we can ensure that the performance of the robust policy under the true noise process is less than the Z hat here, which is the worst case guarantee, right? And we evaluate the performance under the true probability law. Okay, so here Z hat constitutes a certificate or guarantee of the worst case performance of the robust control. Okay, and this result also provides theoretical guidance for adjusting the radius gamma as a function of the number of samples n. All right, so now let me showcase the numerical experiments. So in our simulation, we consider two autonomous control systems. So we have a 2D robot and a unicycle, and we try different algorithms on these systems. And for both examples, the system moves in XY plane. The difference is just how the control inputs are designed. So for the 2D robot, the control inputs are vertical and horizontal velocities. So in other words, the robot can move vertically and horizontally, and even diagonally, with a combination of the vertical and horizontal movements. For the unicycle, the control inputs are linear and angular velocities. So the robot can move either forward or backward from the current orientation of the wheel. Now, let me make some comments on the experiment setup. So to reflect limited data availability, we start each simulation run with an initial estimate of the true noise process using only a single data point. And then as we explore the environment, we will update the approximate noise process as we collect more noise data. So we compare our algorithm, distribution robust path integral, with two existing path integral control algorithms. One is a risk neutral path integral control here. So here we denote it by RNPIC. So this model pretends that the approximate noise process based on the data is the true noise process and solves the corresponding stochastic optimal control problem using the path integral control. The other one is the risk averse path integral control, or RAPIC. And since there are no existing finite sample guarantee for this risk averse control problem in the literature, this risk averse method lacks a clear way to determine theta in advance, the risk aversion parameter theta in advance. So indeed, it actually remains an open question on how to determine the parameter theta. So in the literature, the selection of theta typically involves a trial and error process where a policy from different values of theta are tested in the actual environment until the resulting performance aligns with the modeler's risk profile. However, this experimentation can be costly in safety critical tests. For our experiment, we will discretize the value of theta, and then we will find the best performing risk parameter. So these three figures show 100 simulation runs for each algorithm. So the green trajectories represent successful runs, but the blue trajectories are failures, where the robot hits either the outer boundary or the inner obstacle. And in this table, we recorded the success rate and also some statistics on the arrival times for successful runs. And as highlighted in purple, our scheme here provides significant advantage over the risk neutral and risk averse path integral control algorithms, including a higher success rate, faster arrival time on average, and more consistent and predictable performance because we have lower variance. And we remark regarding the risk averse path integral control, we only present the instance with the best performing theta. Okay, so in contrast, most of the other instances of the risk averse path integral control algorithms generate significantly worse performance than the distribution robust path integral control. Okay, so this actually demonstrates the benefit of optimizing the risk parameter in real time. Okay, so that actually concludes my talk. So just a few key takeaways. So we have shown that the single level reformulation of our distribution robust control problem exhibits similarities with the classical risk averse control problem. And this allows us to use path integral control formulation, which can be numerically solved by Monte Carlo simulations. And then since the path integral formulation can handle quite general nonlinear functions, our proposed algorithm can be used to solve a broad class of nonlinear control problems. And we also discuss the data-driven distribution robust control problem and derive finite sample guarantees and out-of-sample performance. And these guarantees provide guidance on how to scale the radius parameter as we collect more samples. And because of the similarity between the risk averse control and our distribution robust control, we actually provide a new insight into how to control, how to choose the risk parameter for risk averse control problems. All right, so that concludes my talk. Thank you so much. I'll be happy to answer your questions.